Hello, I'm Emmanuel. Welcome back to Economics. We've been considering regression analysis and specifically we looked at the ordinary least square method quite extensively. We've tried to derive the estimators and we even talked about the assumptions as well as the properties. Now we'll be taking a step further by looking at hypothesis testing and confidence interval. Hypothesis testing and confidence interval. Okay, so we recall we worked out a numerical example on using the OLS method. We tried to look at the relationship between consumption and income. Okay, where our dependent variable was consumption and our independent variable was income. And we're able to estimate this regression function making use of the OLS estimators, where this was our slope coefficient, our intercept coefficient, and this was our slope coefficient. This representing the autonomous consumption and this representing the marginal propensity to consume. So what we have here are point estimates. Recall that we made mention of the fact that we've been using the sample regression function. So it's not possible to always make use of the whole observation in our population. So most times we use random sampling to select samples on the basis of which we estimate our regression function. When we take repeated samples, we are bound to get different estimates, different point estimates. In this case now, we made use of 10 observations. Peradventure, we randomly sample again and select 10 different observations. We likely not have these exact same values for our autonomous consumption and our marginal propensity to consume, and that's perfectly fine. Recall we said that with the OLS estimators we expect some sort of variation in our estimates, but we expect that on average the average value of these estimates we get will equal the true. So that's fine. Rather than working with point estimates, we can as well specify some sort of interval and say that, for instance, our autonomous consumption, I guess we use million, so this is 2.447 million. So we expect that when income is zero, when there's no income, consumption will still be about 2.447 million naira. So rather than just giving a point estimate, we could as well say that we expect autonomous consumption to be between say 1 million naira and 3 million naira, right? So we could specify an interval for the estimators rather than using point estimates, and that brings us to the confidence interval. Is an interval around the point estimator where the true parameter value lies. So rather than just giving points estimates, right, we could sort of specify an interval and say, okay, we expect consumption to lie between this, autonomous consumption rather, we expect marginal propensity to lie between this. You see, this includes our actual, what we estimated, 2.447. So we could walk around and just estimate a sort of interval that most of the times, I wrote probably, and I'll explain that shortly. Most of the times we expect that our true parameter value will lie in that interval most of the time. Let me come to that again. You recall we're making use of repeated samples, so you get different point estimates, right? And if you are getting different point estimates and different standard errors for these estimates, you'll be having different intervals in repeated sampling. So we expect, and that's where the issue of probability comes in, that assume your confidence interval is say a 95%. Assume your confidence interval is 95%. We expect that 95% of the times you took repeated sampling to estimate your confidence interval. We expect that 95% of the times that confidence interval will capture the true parameter value. It will capture the true parameter value, and so it's in a way sort of reliable. And that way we describe the confidence interval is, and usually this way is described, is using 1 minus alpha, where alpha is the significance significance level. So we'll be discussing that as we go on. Okay, next is hypothesis testing. So rather than just estimating points, getting your point estimate and also estimating the sort of interval, we could also test, okay, that we've discovered that minor price to consume is 0.509. Is this different from an arbitrary value or something that has been found in previous studies? So we are testing if what we found is compatible with some stated hypothesis. For instance, now a research has been done and they found minor prices to consume in Nigeria to be 0.7, and now after we've carried out our own research, we've gathered data, we got a regression line, and we're discovering it is 0.509. You might want to ask, you might want to just test, is a 0.509 statistically different from the 0.7 that was found earlier? Is this something that could have occurred by chance, and so we still accept the hypothesis that Nigeria's marginal prices to consume is 0.7, or we do not accept, or we reject, or we do not reject? So that's the domain of hypothesis testing, and we'll be walking through the same example we looked at, where we estimated this function. We'll be taking it a step further, and we'll try to calculate confidence interval for beta 1 for the intercept coefficient that we estimated and the slope coefficient. We'll try to estimate the confidence interval for them, and we'll also use the test of significance approach to also test to see if these values are significantly different from the arbitrary value we're using is 0. So we call our null hypothesis for each of them. We'll discuss about this in a while. We'll call it 0, and we'll try to test to see if what we found is significantly different from 0. So in estimating our confidence interval, we make use of the assumption that our estimators, beta 1 and beta 2, are normally distributed, and this is not far-fetched. We record the assumptions of zero conditional mean value of the disturbances, that's of our residual, and also constant variance. So our residuals are normally distributed with mean of 0 and variance of sigma squared. And if our residuals are normally distributed, it follows that the dependent variable to y is normally distributed. And among the properties of OLS that makes them blue, best linear unbiased estimators, we mention the fact that the OLS estimators are a linear function of a dependent variable y. So if y is normally distributed, it also follows that beta 1 and beta 2 are normally distributed. And specifically, beta 1 is normally distributed with mean of the true parameter and variance of summation xi squared sigma squared over n summation small xi squared. Okay, and in same vein, beta 2 is normally distributed with this. Okay, so assuming a normal distribution, it's very easy to estimate our confidence interval. So we can make use of the z distribution, which is normally distributed, or the t distribution, which is also normally distributed. But in this case, we're making use of the t distribution. And that's because the number of observations we are making use of here is less than 30. Usually, when it's above 30, you could and it's normally distributed, you could approximate using the z distribution. So here we are just making use of 10 observations. So we'll make use of the t distribution, and in checking the values, in sort of estimating our confidence interval using the t distribution, and that term is also introduced here. It's called the degree of freedom. And the degree of freedom is simply the number of observations n minus the number of parameters k. Right. So in what we'll be doing briefly, the degree of freedom will be 10, we're making of 10 observations, minus 2, we have two parameters, beta 1 cap and beta 2 hertz here. So we're estimating that our degree of freedom is 8. So we make use of the T distribution with the degree of freedom with 8 as the degree of freedom in estimating our confidence interval. Another thing I also want to mention quickly is that we'll be using a significance level of 5%. Significance level of 5%, and so that means our confidence interval is a 95% confidence. We'll be estimating 95% confidence interval. The confidence level is 95%. The confidence quotient, another way you could call it, is 95%. Okay, so we'll be working with that in estimating our confidence interval, and as well in testing the hypothesis to know if what we estimated is statistically significant, statistically different from an hypothesis, which we'll be calling 0 here. So in estimating our confidence interval using the T distribution, we usually make use of what we call the T statistic, and which we get the value of the T statistic and then compare to the normalized T distribution, which we can always get from our statistical table. So this is where the distribution looks when it is normalized, and we transform whatever the parameters, the estimates we are trying to sort of check and try to estimate the confidence interval for. We transform whatever it is in each of beta 1 or your beta 2. We transform it rather to the T statistics and then compare with what we have in the table to decide whether to accept or reject the null hypothesis if we are doing hypothesis testing. And also, even when we are estimating our confidence interval, we transform first to be able to estimate our confidence interval. So in the normal, when it's normalized, this portion represents the acceptance region. It's sort of like the 95% confidence interval. So we are saying that it's the confidence interval when it's normalized is between minus 2.306 and 2.306. And now note that this is where the degree of freedom is 8 and the level of significance is 5. What we have here is the 5% level of significance, the cutoff, and because it's a two-tailed test on both sides, we'll be sharing the 2 points. We'll be sharing it, so you have 2.5%, 2.5. So both represent your level of significance, and this represents your confidence quotient, your confidence level. And when you sum it together, it's 100 because that's the whole area under the normal distribution plot. So depending on the level of significance you choose, some might decide to work with a 1% level of significance, and that means a 99% confidence interval, 99% confidence level. And depending on the number of variables, number of observations you have, and the number of parameters, your degree of freedom too could vary. So working with a 95% confidence quotient and degree of freedom of 8, checking the tables, our T value will be 2.306, and so on the other side minus 2.306. So to compare, then we convert first of all this T statistic, the estimates we have are beta 1 and beta 2. This could be beta 1, this could be beta 2, depending on which T statistic you are trying to estimate. So you first of all estimate for beta 1, compare with the cutoffs, with the critical values, compare, then decide to accept or reject. Okay, so if we're doing the hypothesis testing, choosing to you only accept when your T value falls between this region. So you accept, in quotes, usually statistics, they don't say accept the null hypothesis, they just say you do not reject the null hypothesis. So but let me just say accept so that you get the term easily. So you accept the null hypothesis when it falls between this region. So for instance, if we calculate our statistics and we get it to be something like a 2.1, right? So that will be somewhere around here. So it falls in the acceptance region, so we do not reject the null hypothesis. But if our T statistics is greater than 2.306, say a 2.7 or 10 point something, or a minus 5 point something, it falls in the rejection region. So we reject null hypothesis straight away. So that's about using the statistics when it comes to hypothesis testing. When it comes to the confidence interval, the way it works is to estimate your confidence interval. You make use of, say, for beta 1 now, we want to estimate the confidence interval for beta 1. Our confidence interval will simply be by estimating confidence interval for the true population, true parameter value. Our confidence interval will be what we estimated plus or minus the t value. Now, what we are making use of at is 0.5 significance level and 8th degree of freedom. So at t at this point, let me just call it 2.306 times the standard error of beta 1. And same thing too for beta 2. The confidence interval will be this, the estimated beta 2 plus or minus 2.306 times standard error of beta 2. Okay, so the reason why it is this is not far-fetched. So actually, let's walk back. Let's assume we've normalized this stuff, right? We have the t distribution, and we're trying to walk back to what our true population, our true parameter when we consider the whole population will be. Let me just call this beta 1. Okay, so we've discovered our t stuff to be 2.306. is within, that's for the 95% confidence quotient, given that degree of freedom, is equal to this estimated beta 1 minus beta 1 over the standard error of beta 1. So if we try to solve for this, what we'll be having now is 2.306 times the standard error of beta 1, right, is equal to this minus beta 1. And so the true beta 1 now will be this plus 2.306 times the standard error of beta 1. So this is where when it is statistics is 2.306. So if you take for the other one too, or when it is a minus 2.306, you arrive at something like the beta 1 is equal to this minus 2.306 times the standard error of beta 1. So those are the two values. So your confidence interval then will be that the true beta 1 ranges between this, because this is cutoff, ranges between this and this. So we'll do that for our example shortly. So this was the same example we looked at in the previous video, where we looked at try to estimate the relationship between consumption and income with this function. So it's the exact same table, and that's the beauty of using the derivation approach, where we make use of small x represents x minus capital X minus the x bar, and the same thing with this. The formulas are sort of more compact, and you can still make use of that same table to work and get this stuff. So the only thing that was added now was this column for the squared of income, or the income observations, and that's because we need the formula here. Recall the goal is to compute our confidence interval and also do the test of significance, but we need the standard error of beta 1, standard error of beta 2, and this formula for variance. Standard error will just take the square root of this to arrive at, we take the square root of variance to arrive at our standard errors. So we need summation xi squared, and that is why I've created this column, and it's simply by squaring this. So 8 squared is 64, 10 squared is 100, and down. We've computed this before, so you could look at previous videos to just be more clear on that. Okay, and we have every other thing we need. We know our n is 10 observations, 1 2 3 4 5 6 7 8 9 10. We know, okay, so we know this already. We know summation xi squared 330, and every other thing. So the only thing left for us to be able to compute this, we already know the estimated values for this: 2.447 for beta 1 and 0.509 for beta 2. So the only thing left for us to be able to compute the standard errors and then do the test is this value, sigma squared, the variance of the population. And actually we don't know the variance of the population usually, so we make use of dependent variable now. So we try to estimate this, and it's estimated as the residual sum of squares divided by the degree of freedom. In this case, we are making use of two parameters, so I just want to call it k or 2. If in a multiple regression case where we have two or more independent variables, we could be having up to 3 parameters or more. So in this case, our RSS over the degree of freedom. And recall that we said TSS is equal to ESS plus RSS, and so that means that our RSS will simply be TSS minus ESS. TSS is summation y squared, which you can easily get 18.9, and our ESS, we gave a shortcut that our ESS is actually this summation y hat squared, and we worked out a faster way of working that, so we called it this. So beta 2 squared summation x squared. So squaring our beta 2 and multiplying by summation xi squared, which is 330, will give us the ESS. And so when we just subtract this from this, we get our RSS automatically, and we can divide by 8 in this case, where the degree of freedom is 8, 10 minus 2, 8. We divide by 8 to get our population variance, or the variance of the error term. Is the variance of the error term is also the variance of y, of the dependent variable. So, and once we have that, we can easily plug it in to get our variance of beta 1, and as well get the standard error, and we'll be able to calculate the confidence interval and also run our test to see if the estimates we generated are statistically significant.
Hope you enjoyed the video you just saw. If you want more of our videos, please make sure you subscribe to the channel and click on the notification bell. Now, there is a way to enjoy to make the best of our YouTube channel, which is to go to the playlist section of every video or of every topic. So what you have to do is just type Economics on YouTube. When the page displays, make sure you subscribe. A bell button appears immediately, so you click on that bell button. Then go to the playlist section. So you're going to see videos, playlists, description, and all of that. So just go to the playlist section, and whatever topic you are looking for, look for the playlist and click on the video. Now, our playlists have the classes arranged in a very chronological manner. So if you want to see a class on ISLM, so it starts from the beginning, the simple ones, to the difficult to the complex ones. So if you want to see a video on, let's say, elasticity of demand, so you start from what is price elasticity, so from there then to the basic ones, and on and on. So I'm just telling you that in case you really want to make the best of this YouTube channel. And there's also one thing that I want to add, which is that our YouTube classes may not be enough for you. You may want a regular interaction with the tutors and all of that. So what you just have to do is to check the description of the video. You are going to find a WhatsApp link. So, but before you do that, I really have to tell you that clicking that link is going to lead you to one of our schools. It's going to lead to some of our schools. So we have MOG School of Economics on WhatsApp, and we make use of our YouTube channel to run the groups. So the classes are paid for, so you're meant to pay for them. So to join our Econometrics school, so that is 2,500 naira per month, and to join our Microeconomics or Macroeconomics schools, so that is 2,000 naira per month. We also have we don't have classes, or we don't have schools of mathematical economics, because Microeconomics has its mathematical aspects as well as macroeconomics. So the mathematical aspect of macroeconomics is treated in the macroeconomics school, and the mathematical aspect of microeconomics is treated with the microeconomics school as well. So I'll see you next time. Thank you very much for watching.